Now let us learn about the topic SAP HANA High Availability and Disaster Recovery, which is the HADR technique from SAP HANA. By high availability, we mean having high availability of the SAP HANA solution that the customer is using. And how do we achieve this high availability is a concern. And high availability is always implemented within a data center. Now coming to disaster recovery is a technique which is implemented across the data centers. It is a procedure which supports any disasters within the system or at the operating system level or in the data center site. If there is any prolonged disaster of the data center which is hosting the solution, that is which is hosting the server where the SAP HANA solution is installed, then we will use the disaster recovery techniques to recover the system with minimal data loss and with minimal time. So I repeat, high availability is a solution which is implemented within a single data center to have continuous availability of the system, whereas disaster recovery is implemented to resolve any unplanned disasters, could be of a data center. So this is implemented across the data centers, that is between two data centers. Firstly, let us understand the definitions of high availability and disaster recovery. Also here we will be learning about another procedure called fault recovery. See, SAP HANA is fully designed for high availability, that is supporting a broad range of recovery scenarios from various faults. And these faults could be a simple software errors to disasters that decommission an entire site. So as I said, to achieve high availability of the system, we implement these procedures which could support the recovery scenarios from various faults. These faults could be a simple software issue, a software bug due to which the system goes down, or due to some crash at the operating system level, or crash of the hardware, crash of the network, or could be as big as a disaster that decommission an entire data center site. And what is high availability? High availability, by definition, is a set of techniques, engineering principles, or practices and design principles for business continuity. So, combining these three to support business continuity is what high availability is all about. And it is achieved by eliminating single points of failures, that is called as fault tolerance in other words, and providing the ability to rapidly resume operations after a system outage with minimal business loss, called as fault resilience. So high availability is nothing but a set of techniques, practices which are followed to avoid any sort of single point of failures and thus provide continuous availability of the system to support the customer or to support the business without having much business loss and with minimal amount of time. So at any system outage situations, we implement these high availability techniques possible to recover the system from this outage as fast as possible. And now, and now moving on to fault recovery. Fault recovery is termed as the process of recovering and resuming operations after an outage due to a fault. So this again points to a fault, an outage due to a fault, where we implement this recovery procedure of uh, recovering the solution and resuming the operations. So in this fault recovery support, there are two techniques supported. One is termed as the service auto restart and other is termed as the host auto failover. So basically in the event of any software failure uh, that disables one of the configured SAP HANA services, be it index server, name server, or access engine server, the service will restart by the it will be restarted by the SAP HANA service auto restart watchdog function. So any service which goes down will be monitored by a watchdog function called auto restart watchdog function within SAP HANA service, which automatically detects such failures and restarts the stopped service process. So upon restart, the service loads data into memory and resumes its function. So the data remains safe and this service recovery takes very little time in this case. So this is supported with the help of the restart watchdog function, which always keeps running and monitoring all the services of SAP HANA. And next technique is host auto failover. Host auto failover is a basically local n plus m implementation. It's a fault recovery solution which can be used as a supplement or probably regarded as alternative measure to the system replication solution. I'll come to what is system replication. It's a part of disaster recovery. So here host auto failover is normally regarded as an alternative measure to the system replication for fault recovery solution. Here, one or more standby hosts are added to SAP HANA system and configured to work in standby mode. That is basically with the use of multi-node systems. See, if we have only one SAP HANA instance for a system, it is regarded as single node system. But we can add multiple instances, that is multiple hosts. Say host 1 is already running, we can add host 2 with another instance, host 3 with another instance, so that host 2 and 3 can act as the standby hosts or standby instances. And yes, since they are standby instances, they are configured to work in standby mode. And as long as they are in standby mode, the databases on these hosts do not contain any data and do not accept requests or queries. They are just kept as a standby instance, just for the purpose of taking over in case of any failure of the primary instance, that is first instance on host 1. So they do not accept any queries, they do not process any request. And by host auto failover, I mean in case of failure of host 1, this automatic failover from crashed host to standby host is triggered. That's how the business continuity is achieved here. So this was about fault recovery. Now coming to disaster recovery is a process of recovering operations after an outage due to a prolonged data center or site failure. Preparing for disasters may require backing up data across longer distances, and thus it is proved to be more complex and costly. So basically, in simple terms, disaster uses a set of techniques for recovering the operations after an outage could be at the data center or at the site. So basically, disaster recovery uses certain techniques which is both at hardware and software level, that is managed by both hardware and software, which uses certain capabilities to keep the RTO and RPO values as low as possible. What are these RTOs and RPO values? You can see the picture here where a system is operational in normal condition, and this is the point where a backup is triggered. And going ahead, we see a crash which causes an outage of the system and the operation ends there. So the time between the previous backup and the crash point is regarded as the RPO. By definition, it is the maximal permissible period of time during which operational data may be lost without ability to recover. So basically, in simple terms, time between the last backup and the crash is termed as the RPO. And next, from the crash point to the point where we recover the system, that is to the time when we recover the system, is termed as RTO. By RTO, we mean it is the maximal permissible time it takes to recover the system so that operations can resume. So we have to make sure RPO and RTO values are kept as low as possible. So to achieve this, disaster recovery uses various techniques. One of the techniques is the backup and recovery procedure, and other techniques where continuous replication to another data center, that is continuous sync to a system kept in another data center, is performed using the system replication techniques. And this system replication technique is operated in different modes like synchronous, asynchronous, synchronous in memory, which offers different advantages, and also with respect to cost would be, some would be costly, some would be inexpensive, and could be a viable option too. Now let us understand what is redundancy. See, the key to achieving fault tolerance is to eliminate single points of failure by introducing redundancy. So basically, in simple terms, redundancy would be a technique applied to achieve fault tolerance in cases where we have single points of failure. And these redundancy techniques are offered by SAP HANA appliance vendors, and they are offered at different levels to avoid outage due to component failure. These levels are hardware redundancy, network redundancy, data center redundancy. So in case if there is a crash, there is an outage due to hardware issues, then hardware appliance which is delivered from the vendors are designed with multiple layers of redundant hardware components and subsystems so that in cases of failure of the hardware, the system gets attached to a backup hardware, another hardware, to have continuous availability of the system. And moving on, network redundancy. What is network redundancy? To achieve network redundancy, there are redundant networks, network equipment, and network connectivity to avoid any sort of network failures which affect the system availability. So, in case of any unknown network failures, this technique, that is network redundancy technique, allows to switch over to a possible backup network so that the continuous availability of the system is achieved. And next is data center redundancy. We all know that data centers host SAP HANA solutions. That is, they host the servers where the SAP HANA solutions are installed. So these data centers are equipped with UPS, that is uninterrupted power supply and backup power generators, redundant cooling systems, and multi-sourced providers of network connectivity and electricity, just to achieve operational availability in the presence of individual failures and significantly reducing the probability of a business impacting outage. So, data centers are equipped with continuous power supply, power generators, and continuous network connectivity so that they keep running the system. In case of any unavailability, which is very rare to happen, it should recover immediately from that unavailability so that business impact is minimal. So, overall, by achieving different levels of redundancy, we can combat to any sort of outage due to component failure. That is why we implement these levels of redundancy as a safety measure. Next is about knowing what is scalability. Scalability has a number of aspects that needs to be considered, such as scaling data, performance, applications, and hardware. So by this we mean scalability is a technique or a procedure which is used to scale up the server, scale up the hardware, or scale out the system. That is basically SAP HANA supports is scale up and scale out approaches to support scalability technique. By scale up, we mean increasing the size of one physical machine by basically increasing the amount of RAM, CPU available for processing. So, technically, what it means is if in case we have a system running on a server which is furnished with certain amount of RAM and certain number of CPUs. If the size of this server, that is size of this hardware, is not enough to combat, that is to support the increase in the data growth, we plan to scale up the server. That is, we plan to increase the amount of RAM and number of CPUs to support the data growth or to support the growth which can be estimated for some time in the future. So we have to forecast on the data growth that we would have and scale up the server accordingly so that this reduces the impact on the business, be it with respect to performance or certain times unavailability also, because if the consumption of RAM is overshot, then we see that we will have out of memory issues and the proper functionality of the SAP HANA system cannot be achieved. So this supports performance as well as continuous availability of the system. Now moving on to scale out. Scale out is basically achieved by combining multiple independent computers into one system. So this means it's an SAP system with multiple servers over which it can distribute the load. As I said, when we have a single node, if we analyze or if we can forecast that data growth is going to be big, there, there are going to be large tables within the system, or there are large tables already present in the system, then it makes sense to add multiple servers, add few more servers which can distribute the load. By distributing the load, you can achieve better performance and also have quick response to any sort of request. Say for example, we have a few large tables within the system. What we can do, we can break these large tables into smaller chunks and distribute across multiple servers so that they can operate on these chunks whenever there is a request to operate on these tables, and thus provide the response as quickly as possible. So what this is, once we have reached the physical limits of a single server, we can scale out for multiple machines to create a distributed SAP HANA system, thus achieve the data load distribution. So as I said, a distributed SAP HANA system is a system installed on more than one host, that is having multiple instances. Basically created to deal larger amounts of data or for higher availability also. How? With these multiple instances, we can have few instances to be active and few instances to operate as standby instances. So in case of any failure or outage of any of these active instances, these standby instances which are not operating on any request can take over the role of these active instances and resume the operations immediately. Thus we can achieve high availability by implementing the distributed SAP HANA system technique. And here each instance has an index server, a preprocessor, and a name server component. Whereas only the first instance, only the first node will contain the statistic server and the access engine server also, which actually exist only once per system. So only the first instance will have all the five processors, all the five components of the server, whereas the second, third, fourth, and further on instances will have only index server, a preprocessor, and a name server. We will come to more details on how we build this distributed system and how it operates. Now let us learn about high availability. Let us learn more into what is high availability and how it is implemented. See, we all know that high availability features are critical to customers and they are implemented at the core of the design of SAP HANA. Since its inception, we have this technique available, and working closely with partners, customers can benefit from combined solutions to reduce and minimize hardware, software, or network failures as well. So, with all this, high availability is a technique which enables the failover of a node within one distributed SAP HANA appliance in simple terms. So considering this as an SAP HANA appliance, if one of the node fails, other nodes will take over the role of the failed instance. So as I said, in a multiple node system, that is a distributed system, we can make only few instances. Say here, host 1, host 2 can be kept as active instances, host 3 can be kept as a standby instance to take over in case of failures of host 1 or host 2. So thus achieve continuous availability in case of even if one of the node fails. And this failover uses a cold standby node and gets triggered automatically, as I said. By cold standby we mean it is not operating on any request, but whereas it gets loaded with the data and logs of the active instance, and thus will be to the latest point of time so that it can be recovered immediately with very less RTO value. And HA features are supported by native capabilities for recovering from all sorts of be it hardware, software, network failures, and all sorts of failures ranging from minor faults to major outages. In this, we have certain techniques of achieving high availability. As I explained, automatic restart of services with the help of SAP HANA watchdog function, wherein SAP HANA core services are continuously monitored with the help of this watchdog function. And in case of failure, that is stop of any of these services, the watchdog function, the restart watchdog function will automatically restart that particular service and makes it to run continuously. And next is about fault recovery from host outages. This is again achieved by having clustered databases, that is multiple servers, where in case of any event of component server failure, we can have continuous availability of the operations. And next is about achieving near zero downtime upgrades. Consider we have a productive system and we want to upgrade it to the latest software level. How is it achieved with minimal business loss? This can be achieved by using distributed system again. How? We can have a secondary instance which is getting data from primary instance, which is the main productive instance, which acts as the standby instance. Secondary would act as the standby here, and this gets continuous data and logs from the primary so that it is at the latest level at any time, any point of time. And here to perform the upgrade, we would first choose the secondary instance which acts as the shadow instance and do the upgrade there, then make a takeover. That is takeover in the sense secondary would take over the role of the primary instance. It becomes the productive instance. And then we can patch the productive instance to the required target software level. And once productive instance is ready with the required target level, it is made to take over the role of the productive instance. That is, a failover is done again so that the original productive system takes the role of the productive instance again. So basically, from NZD, that is near zero downtime upgrade approach, we know that we do the upgrade with the help of a shadow instance so that we can reduce the impact on the business. So here a shadow instance is created and then upgrade is done on the shadow instance, and the business would have to go down only for a short period of time during the downtime phase where the actual switch takes place. And after this again you can quiz the production data, that is any data which is to be taken over can be quizzed, and then we can have the productive system available again. So with the help of distributed system, even the near zero downtime upgrades are achievable. Now let us understand about what happens when a name server failure or an index server failure occurs. See, in a distributed system, this name server acts as a central component and it knows how data is distributed across multiple instances, multiple active instances. So basically, name server would know which tables, table replicas or partitions are located on which index server. So basically, if an index server gets any request, it will first contact the name server to understand where is this data stored, in which instance is this data stored, because after data distribution this data can be kept on any instance. We can move different parts of data into different servers, basically followed by a partitioning technique. Could be a database partitioning or a table partitioning technique. By database partitioning we mean we can divide set of tables to be placed on different instances. By table partitioning, we can divide a particular table, split a particular table itself, and keep its chunks on different instances. So name server would know details about these chunks, so that if index server gets a request, it can talk to name server and get all this information. And index server contains all the data and processing components. And each index server is a separate operating system process as a whole and has its own disk volume. So when processing database operations, index servers may need to forward the execution of some operations to other servers that probably own this data involved in this operation. So we should know that in each SAP HANA system, there is one master index server, and it stores the metadata and contains the master transaction manager that coordinates distributed transactions involving multiple index servers. So if database clients send any sort of request to index server, it contacts the name server to know the details of the data. So basically, the name server which holds the topology information, that is, it holds the information about each data. But name server are regarded as master and slave name servers. As I told you, the name server which is acting as the master will actually replicate the information to all the other name servers, all the slave name servers also, because it is not ideal for the index servers of other active servers, that is other than the master active servers, which are regarded as the slave index servers, to always talk to master name server to get the topology information. So to ease this operation, master name server will replicate the topology information to each name server present in the system, so that the local index servers can talk to local name servers itself to understand how and where the data is stored. And the master name server will have its own persistence, whereas the slave name servers will have no persistence here. We should keep that in mind. So only in the first host we will have, if this is acting as the master, we will have persistence of name server, also index server, access engine and statistic server. Further on, second instance will have the persistence of index server only, and host 3 again will have the persistence of index server only. And now let us understand, in case of failure what happens. In case of master name server failure, another of the remaining name servers will become the active master. So that means if this fails, any of these name servers, either host 2 or host 3's name server, will take over the role of the master name server. That is, it will attach to the persistence of the master and operate as the master name server from there on. And what happens if index server failure occurs? If index server failure occurs, master name server detects an index server failure and executes a failover. So during this failover, what happens? Master name server assigns the volume of the failed index server to the standby server. Say this host 3 is acting as the standby server. In case if the index server of host 2 goes down due to some crash, then the master name server will identify this. Then what it does, it will connect the index server of the standby server, that is host 3, to the volume, that is data volume and log volume of host 2, that is failed index server, and this presumes as the active index server from there on, which will operate on the data. So that's how we achieve the high availability using the distributed SAP HANA appliance. Now let us understand how to set up a distributed landscape. We all know that distributed landscape is set up by installing multiple instances, that is by transforming a single node to a multi-node system. So to set up this, we have to meet a set of prerequisites. First, system has to be installed, that is a single node system should exist with its server software, but this server software should be on a shared file system so that even other instances can access it, and this system should be running. Next, we should log on to the new host with the root user. New host where we will add another instance where we need to log in with root user, and we should make sure the shared file system is mounted on every host, and we should know the user ID of the SID ADM user on the master system, that is the first host, and this user ID should be free on the new host as well. And similarly, group ID of SAPSys group should also be free on the new host, because the user ID and the group ID will be used by the STB add host program on the new host. And the instance number of the master instance, that is the first instance, should be free on the new host as well, because since we will be using the same instance number, should make sure the instance number is not occupied by any other application or any other instance in the new host. This should be free and available. And the procedure is, we have to log in to the new host with a root shell, navigate to this path, that is installation path, SID global STB install bin, where the STB add host program is stored. Launch the STB add host program. It will ask us few details about the instance number, system administrator, user, installation path, data path, log path, and then we can proceed to add another instance. And once we add, this is how it would look technically. Here it shows three instances: HANA 1, HANA 2, HANA 3 are the three hosts hosting the instances, and SID is DB1 here, and the instance number is 01. We see that, see, same architecture is followed in each instance. It should have the same SID, same instance number, and it should have the same system administrator. And as told, it should have a shared software directory and shared persistence directory too. Okay, see, group access and user also remain the same. And upon setting up a distributed database system, this is how the data and log volumes would look like. As I told, only the first instance, that is the first host, which is where the parent directory is mnt00001, which is the master server, will have the persistence of all the four components: name server, index server, statistic server, and access engine. Whereas the second, third will have the persistence of only the index server. So if you add one more instance, which becomes mnt00004, we will again have only the index server persistence there. So in these, we can have two instances to be active and other one as the standby. Or if we don't want this high availability, just need only the data distribution, then we can operate on all the three instances. It again depends on the business requirement here. And to ensure that we can recover the system to a point in time after we have added the host, it is recommended that once the distributed setup is completed, we should stop the productive operations until the addition of the host we should stop the productive operation and perform a new complete data backup. So during the time where we had multiple instances, we should make sure we stop the productive operation, and as soon as it is completed, trigger a complete data backup so that at any unplanned circumstances where the system outage is seen, we can recover to this point at least. Now let us learn about data distribution. So after we have installed a multi-node system, a data distribution system, we have to perform the data distribution, and how automatic data distribution would work is what we have to understand. SAP HANA supports different ways of distributing data between multiple index servers in a system. As I explained earlier, we have to use partitioning techniques here. That is, first one would be database partitioning, where different tables can be assigned to different index servers which normally run on different hosts. Technically what happens is, consider a large table which has to be broken into small chunks. When a non-partition table is created in a distributed system, it must be assigned to one index server, right? By default, new tables are distributed across available index servers using a round robin approach. For example, if there are three available index servers, say A, B, C, including one master, the first table created will be located on server A. Next one will move to server B. Next one will move to server C, and so on. So that's how the partition of tables takes place. That is partition of not a particular table, but different tables would take place. And in addition, it is also possible that we specify explicitly that a particular table or a partition be created on a specific index server. We can choose the index server, that is which instance index server should be used to locate this particular table or a partition. And we can define up to 3 master name servers, and during the startup of the system, one name server is chosen as the active master, and this active master assigns a volume to each starting index server, or in case of standby servers, there is no volume assigned at all. So that was about partitioning different tables. It follows a round robin approach, or you can mention explicitly where you want to store. Coming to table partitioning. Here, a single table can be split in a way that different rows of the table are stored on different index servers. So by this I mean, consider a large table, which I was to explain earlier. This large table can be broken into small chunks, that is row wise, and different portions, that is different rows, can be kept on different index servers of the multi-node system. And thus, if an operation demands to operate on this table, that is on different rows of the table, it can be achieved by using parallelism. We can operate on different index servers at the same time and thus have the quick response here. And how do we do this redistribution? After installing the multi-node system, that is after installing multiple instances, that is transforming a single node to a multi-node, we have to log into HANA Studio, switch to landscape redistribution tab, select the optimize table distribution operation. Click on execute there, which will initiate a new table redistribution run. And this new run will first calculate the table partition distribution based on the table underscore placement configuration records. And this is done across all the scale-out system slave nodes. Okay, master as well as slave. And this table partition redistribution will create a plan with a calculation and is displayed. And every redistribution activity is displayed with the information on table name, partition, old partition specification, new partition specification, information about current host, slave node, and new host. So the plan would contain detailed information about the table name, partition, and specification of old host and new host. And then clicking on execute after you confirm this plan, this would run to distribute the data across multiple instances. And based on the size of the data, that is size of the system, this can run for some time. Could be a normal run would take more than 12 hours. Again, it depends on the network speed here across the servers. And we should note one thing, we should never stop or interrupt a table redistribution run execution at any point of time, because this can lead to corruption of the data. So make sure don't stop or interrupt any table redistribution plan. Now let us move on to understand the next technique. We have learned about high availability now, and now let us move on to disaster recovery. By disaster recovery, I have already explained how to achieve, or how does disaster recovery support in any unplanned outages at a data center or at a particular site. So basically how disaster recovery across data centers can help in resuming any business operation. And disaster recovery is achievable by three techniques, or I would say three levels again. Firstly, it is using backups. We know that SAP HANA persists two types of data to storage. One is the transaction redo logs and other is the data changes in the form of save points at regular intervals. What is this transaction redo logs? Transaction redo logs are the logs which store the change, which record a change. We know that to make any transaction durable, it is not required to persist the data changed, but it is sufficient to persist the redo log. And upon any outage, most recent consistent state of the database can be restored. How? By replaying the changes recorded in the log. That is redoing completed transactions and rolling back incomplete ones. Thus, we can recover the system to the point of time which was stable. And a save point is a periodic point in time when all the changed data is returned to storage. In the form of pages, it is returned to the storage. And what is the goal of performing save points? Goal of performing save points is to speed up the restart. See, when starting the system, logs need not be processed from the beginning, but only from the last save point position. Say I do a data save point now, and 2 minutes from now, I see a crash. So from this save point, whatever redo logs are present, only they are to be played to reach a point which is close to the crash point. So that's how this save point can help in restarting the system by recovering to this save point and then playing the redo logs, which are very minimal. And this save points are coordinated across different processes and instances of the database to ensure transaction consistency. So basically we have to freeze a save point in the terms of snapshots which are regarded as data backups, and then use these snapshots to recover the system to a specific point in time. and these backups should not be kept locally but should be shipped to backup servers to safe locations, so that in case of hardware crash or disk crash, we will not lose the backups. Backup servers which are more stable enough can host this backups, and then in case of any failures we can fetch this backup and recover the system. Next is about storage replication. What is the storage replication? It is a solution in which continuous replication of all persisted data is possible. That is, with the help of storage techniques, you can see here, which is also termed as the storage mirroring, we have continuous replication of data and logs from one data center, which is data center 1, to the other data center. So using this continuous replication techniques, we have the data copied to other data center which would act as the standby data center in this scenario. We should keep in mind this is the storage level replication solution, which offers a backup of the volumes or file system to a remote networked storage system. And there are various replication techniques available: synchronous, asynchronous, synchronous in memory. We will come to more details about that. Next, let us learn about system replication solution. System replication solution is a solution again which offers continuous data and log shipping, that is continuous replication of persisted data. Here we transport delta data and log continuously on the database level and do not need features on the storage level. See, if you see the picture here, we don't need storage level solution here, but using the database kernel, HANA database kernel, at the database level we ship the data and logs, which is the delta data and logs, to a safer location. So here we will not use any vendor storage solution, but we will use the features of SAP HANA itself. So that was all about different techniques which support the disaster recovery. Now let us learn each one of them in more detail. Firstly, let us learn about storage replication solution. So what are the features it offers? It provides continuous replication, that is live replication of all persisted data through a storage level replication solution. So using the features offered by hardware vendors, different hardware vendors present in market, storage level replication, that is directly from the storage, the data and the redo logs are pushed to the secondary storage, that is to another data center. This happens continuously at the storage level, and depending on the network speed we can achieve a better or a worse replication. So if the network speed is very good, then we can have a better replication, that is faster replication, and if it is slow, then it is worst. So we should make sure the network speed between the data centers is fast enough, between the storage is fast enough, so that the replication runs faster, and in case of any unplanned crashes, any events like that, we will have minimal data loss. So the positives, the pros are it offers more attractive RPO than backups. We know that you can take backups, ship it to backup server, but that takes quite some time to trigger ship the backups. Whereas since this replication is more of live in nature, we can have a better RPO than backups. The data loss can be reduced and also the recovery can be fast enough here. But the limitation is that it requires a reliable, high bandwidth, low latency connection between the primary site and secondary site, which could be costly enough. And also manual action by administrator to enable fencing. By fencing, we mean once the site A is crashed down, site B takes over the role of site A. Then the client solution should not talk to client A anymore. It should talk to client B direct. I mean, it should not talk to site A, but talk to site B directly. If it talks to both the sites, then there is a mix-up of information and we can have corruption of the data. So it makes sense to enable fencing so that it talks only to site B, and site A, once it is recovered, would act as the replicated storage from there. If possible, we can do a failover again, but before that it should act as the replicated storage, not as the primary system anymore. And there are different techniques of or different modes of storage replication, I would say. Synchronous, asynchronous. In case of synchronous, it is a technique which completes when the locally persisted transaction log has been replicated remotely and it is persisted there also. So by synchronous we mean whenever on site A, that is primary system, if a transaction log is persisted and then by means of storage mirroring it is shipped, replicated to the secondary storage, and once it is persisted there, once a response is sent back to primary system, then it means the replication is complete. That is synchronous storage replication. And this can be implemented only for smaller distances, that is less than 100 kilometers, not more than that. And due to its continuous nature, this storage replication can be a more attractive option, as I said, than backups, as it reduces the amount of time between the last backup and a failure. And another advantage is that it offers better recovery times. And this secondary system can be located near the primary system to serve as a rapid failover solution for planned downtime or to handle any sort of storage corruption or other local faults. Or it can be installed in a remote site also to be used in a disaster recovery scenario. So it can be used other than actual disaster recovery scenario, where it can be used to combat any local faults within the same site. Now coming to asynchronous storage replication solution, it is a solution where the transaction logs are transferred, the persisted transaction logs are transferred, and it will not wait for any response from the secondary system. So once the transaction logs are transferred to the replicated storage, it will not wait until it is persisted and it receives a response. So it sends and then it proceeds with the next operation. So there is no latency in asynchronous, whereas there is some latency involved in synchronous storage. But synchronous storage assures that data is persisted in secondary, whereas asynchronous does not assure. So that consistency is achieved with synchronous with some latency. Now moving on to knowing about system replication solution. System replication solution is an alternative high availability solution for SAP HANA, and it provides extremely short RTO and compatible with all HANA SAP hardware partner solutions. So here what happens is we transport delta data and log continuously on the database level and do not need any features on the storage level. As I explained earlier, this is taken care by the HANA database kernel, not by the storage. So we don't need any solutions from the vendors, but this is taken care by the SAP HANA feature itself. And This employs an n plus n approach with a secondary standby SAP HANA system with the same number of nodes as the active primary system. So the configuration at primary and secondary should be the same. See, you see two instances here at primary, even the secondary should have two instances. So exactly the same architecture is needed to support system replication. But much advancement is now happening to have n plus 1 plus n approach, but that is still to be implemented. And what are the advantages? It offers live replication mode and hence extremely short RTO. And secondary can operate without data preload option, thus consume less memory. There are different replication modes again. As I said, synchronous, asynchronous, synchronous with without memory option also, or with memory option. So if we use without data preload option, we will not keep the memory loaded with data, but it will be empty, and that memory can be used for dual purposes as a dual role. You can set the secondary system as a quality or a development system, and in case of failure you can change the role of the secondary from the QA or dev and recover the operations. As I said, it can be set in multiple replication nodes, and transfer process from primary to secondary is optimized. Lesser transfer amount necessary since it is only delta to be transported compared to storage replication where entire data of the file system and logs are more. In system replication, we should keep in mind it is only the delta data, not the complete data, and the redo logs are transferred. And during the takeover to the secondary side, only a roll forward since the latest data synchronization point is necessary. Only the missing logs at the secondary have to be replayed because it is a live replication, that is live synchronization keeps running. So from the latest data synchronization, only a roll forward is necessary. And limitation is that it requires a reliable link between the primary and secondary site. And future scope of system replication is that data synchronization runs only during the initialization of primary and secondary. The synchronization of data is run only once during initialization. Further on, it is only required to transfer transaction logs to secondary. There is no need of delta data to be transferred. Only the transaction logs are enough from the first data synchronization run. So this can offer fastest takeover times as the logs are already replayed on the secondary solutions. And also, as I say, data in memory is already preloaded sometimes with the preload option on the secondary, which acts as a shadow or standby solution, and the takeover can happen in a very short time with this. And there are some points to note. I would say system replication is not host auto failover solution, and it is not scale out solution too. It is a pure disaster tolerance or disaster recovery solution for data synchronization between two data centers. And this always uses a logical primary and a logical secondary name. When we come to setup, we will understand more about this. And a takeover is probably a making of secondary system functioning as the primary system. That is how the takeover runs. It takes over the role of the primary system, and we can fall back to original setup, that is a takeover from the backup site to primary site can be done again once the primary site is back in full swing. And there are some disadvantages like table and column data cannot continuously be loaded into memory on the secondary side. This is a drawback. And hardware is actively used for QA or dev. As I said, it can play, the secondary can play the dual role. It can act as QA system or dev system along with the standby solution. So hardware gets distributed between this queue or dev and the standby solution. This is one of the disadvantages. Now let us move on to understand the system replication modes available. See, when the secondary system is started in recovery mode, each service component of the secondary establishes a connection with its counterpart, that is, with the primary. And from there on, it will request a snapshot of the data from the primary to secondary. And all log changes in the primary system are replicated going ahead. And whenever logs are persisted in the primary system, they are also sent to the secondary system. That means a transaction in the primary system is not committed until the logs are replicated. So in detail, what it means is we can configure the replication mechanism in different replication modes, and they are mentioned here. Firstly, synchronous. Here, the primary system waits with the committing the transaction until it receives a response that the log is persisted in the secondary. As I said, this mode guarantees consistency between both the systems, but there's a cost, there's a latency in transmission of the data and also the response. Now moving on to synchronous in memory. Synchronous, as I said, is only possible for smaller distances, that is less than 100 kilometers between the data centers. Coming to synchronous in memory, here the primary commits the transaction after it receives a reply that the log was received by the secondary, but before it was persisted. Here, the transaction delay in the primary system is shorter because it only includes the data transmission time. Okay. Now moving on to asynchronous, here the primary system commits the transaction after sending the log without waiting for a response. It does not wait for a response. This eliminates the synchronization latency, uh, but at the risk of minor theoretical data loss during failure, because since it does not ensure that the consistency is achieved, that is, the log is persisted or not, there could be risk of data loss here. And this mode is normally most useful if the distance between the data centers is too high, that is more than 100 kilometers or so. Now next, moving on to synchronous with full sync option. Here log write is successful when the log buffer has been written to the log volume of the primary and the secondary instance. In addition, the secondary system is getting disconnected. The primary system suspends transaction processing until the connection to the secondary system is re-established. So no data loss occurs in this scenario. So using the full sync option, we make sure there is no data loss at all. So in case if secondary system falls down due to some network failures, then primary system suspends any transaction processing until the secondary system is back in action to receive the logs. So thus, using the full sync option, we make sure there is no data loss at all. We want every log to be shipped to secondary to have data safety. Now, where does this mode be stored? There is a system table in the HANA database by name sr underscore register, which stores the type of replication which is implemented. So we can just display the contents of this table using the HANA Studio or the SQL command and see which type of replication is running. And next is about extended system replication. To offer higher levels of availability, we can link together multiple systems in a multi-tier system replication landscape. That is, use multiple systems, use 3 sites here. What happens is, this multi-tier setup, primary system which is on tier 1 and tier 2 as a secondary system, and the replication is running between tier 1 and tier 2 here. Whereas tier 2 uses another secondary, that is on tier 3. So tier 3 acts as the secondary for tier 2. So the data or the log that is replicated from 1 to 2 is again replicated from 2 to 3 for a better safety. So this is like extended solution, and this is more expensive than the normal implementation of replication. So this was about knowing different replication modes and the scenarios they would be implemented in. See here, the installation process is divided into several steps. Basically, as I said, initial start of replication, then incremental data and continuous log replication. So we enable the replication first, register the secondary system, then the continuous replication runs when both the systems are in sync. So in a general approach, the configuration steps are like this. Firstly, the primary system is informed to enable system replication, and secondary database has to be stopped. Secondary database should be installed and it must be stopped. Content will be wiped out during initial load with full data backup later during initial start of replication. So once this is enabled, secondary system is stopped, then it is registered for replication as the secondary system, and this advises the secondary system to connect to the primary system and informs about the attempt to start the system replication standby process. And once the setup is done, basically the setup can be done using two tools here. First one is using the STB nsutil program, which is the command line program which must be run using the SID and user, which makes use of site names as the logical name. And second is using the HANA Studio. Again, this also makes site name as the logical name. This uses the site name as the logical name. So using STBNS util or SAP HANA Studio, we can enable the system replication. We'll learn about how to do this in the coming slides. So once the setup is done, you can verify the status in the HANA Studio in the administration editor. See here you can see the secondary system status. It says all services are active and in sync. And to know more details, you should see distributed systems here. Yes, two hosts, and go to landscape tab. Under that, secondary system status, where you can see all the processes of the secondary system and their status. Now let us learn about knowing how to do the setup using STBNS util and HANA Studio. So as a prerequisite, make sure all the services on the primary site have been reachable by secondary site. As I said, they should communicate with each other. The connection between the counterpart services should be enabled. So make sure they are able to talk to each other. That is, you should make sure daemons are listening to the sockets of the secondary side. So the network connection between the primary and secondary should be enabled properly. And we can probably check this using this command netstat_ptl. And if some services are only listening on local host, they're not listening globally, what you have to do, you have to make a configuration change. Go to configuration tab in HANA Studio, choose global.ini, choose communication, choose listen interface, make the entry dot global as the value for listen interface, and then take a restart. And from there, we are good to start with STB nsutil tool. Here I have mentioned all the procedures of enabling system replication, takeover, how to re-enable the replication once the site A is available, and how to disable the replication when we don't want it. So we'll go step by step. First, let us learn about enable system replication, how to enable it. We have to start site A in mode none and stop site B in mode none. And at site A, use the stbnsutil command with the option sr underscore enable and give the site name, logical site name. Can just give it like site A or primary. And with this, you have enabled the system replication at the site A. Now coming to site B, you have to register the site B as the secondary system. So again use stbnsutil using option sr underscore register with the option remote host is equal to give hostname IP or DNS name of site A and remote instance option again, then give the instance ID and give the mode what you want to select, whether synchronous, asynchronous or synchronous mem. Then give the name of the site B. Name is equal to give it as site B or secondary. So upon completion of this command successfully, you can start SAP HANA and this connects to site A and the replication is in sync from there on. So with this we have set up the replication between site A and site B. Now next let us learn about takeover. If site A goes down, how does the takeover run? See, we should understand that executing a takeover on site B will not influence site A at all. We should not touch site A while doing the takeover. Takeover is done only at the site B. So make sure primary on site A is completely stopped. It is not half available or anything of that sort. So make sure it is completely stopped if you want to do a takeover. Then unbind the virtual IP address. Change the DNS entry to point to site B. And then go to site B. Issue the command stbnsutil with option sr underscore takeover. This will take over the role of primary then. Then bind the virtual IP addresses. And once this takeover is done, make sure you trigger a new backup again for the new primary. So with this, we have taken over the role of primary. Secondary has taken over the role of primary. Now, how to re-enable? Once site A is available in full swing, whatever crash has been rectified and site A is available again, how to enable the replication again? We can use site A as the secondary system now. So at site A, do a new registration again using SR register option. But now remote host will be site B host and remote instance will be the instance ID again from the site B. Choose the mode and give the logical name of site A now. So now primary becomes secondary. Site A is turning to become secondary. So with this we have re-enabled the replication. And how to disable? Think that we don't want the replication now. We don't want disaster recovery anymore. So we have to get both the systems back to SR state none, that is none mode again. So at site B, first we have to unregister the secondary system using SR underscore unregister option. So this unregisters the site B. Then go to site A and disable the replication using SR underscore disable option. So this will disable the replication as a whole. So with this, we have learned how to enable system replication, how to take over, how to re-enable replication when site A is back available, and how to disable replication using stbnsutil. Now let us learn about how to use SAP HANA Studio to set up the system replication. So once we have logged into HANA Studio using SID ADM user or the necessary DB user with the right privileges, we have to right click on the primary system, choose configuration and monitoring and choose configure system replication. So there it will display the set of actions to be chosen. we have to click on enable system replication for primary system. And next we will get this box where we will have to choose a logical name for the primary system. As I said, we can give site A or primary. Then yes, these are the details of the primary system, and choose finish so that the option enable system replication is enabled now. And navigate to site B, right click on the secondary system, choose configuration monitoring there as well, then configure system replication there. That is, register secondary system as the secondary for site A. That is, site B is chosen as site A now. Site A standby host now. So upon clicking this, you are registering site B as the secondary system. You will get this screen where we will give the logical name for site B. You can choose site B or secondary and choose the replication mode. Here synchronous is chosen and give the source system information, that is system at site A. So host name will be host A, which is this, and the instance number will be 01. So make sure we don't go wrong in this. After furnishing the correct details, we can choose to automatically start the secondary system and also initiate full data shipping. So select the checkboxes accordingly. If we want to manually start the secondary system, we will have to uncheck this and then finish the operation and then start the SAP HANA system. But if automatic start has to be done, choose this option, then finish. Then the secondary system is started and is in sync with the primary system where it will receive continuous logs. So this was about setting up the system replication using SAP HANA Studio tool. Accordingly, to perform the takeover, we have the option here, and for unregistering, we have the option here, which can be done as explained, which is similar to STB NSUTL again. Now next, let us learn about fault recovery. As I have already explained this, I will just go through this again. Yes, fault recovery is again to recover a system from faults, from some of the basic faults, and it is supported by two techniques. As I said, service auto restart and host auto failover. With the help of service auto restart watchdog function, we can restart any component service which goes down in the SAP HANA system. So in case of any service which goes down in the SAP HANA system due to any fault, then this service auto restart watchdog will continuously monitor and will restart the stopped service process so that we can resume the operation without any faults in the system. And coming to host auto failover, it uses a local n plus m. Basically, m is like often 1, n plus 1 approach, which is the fault recovery solution. It's an alternative measure where it uses a clustered database. Like one is kept as a standby host, which talks to the persistent storage of both host 1 and host B here. In case of host 1 or host 2 failover, the standby host takes over the role. It attaches to the storage of that particular host and takes over the role as the active server from there on. So this, using the standby host in the standby mode, can achieve host auto failover. Next, let us learn about zero downtime maintenance. I have already explained how we do zero downtime system upgrade. Let us understand how do we achieve this. What are the commands we use to achieve this? So as I have already explained, I would repeat, near zero downtime approach is applied here, where zero downtime maintenance is used in case when we want to do upgrades of the software.
or the hardware as well. Say in case if latest hardware or latest software levels are to be reached, we can make use of this zero downtime maintenance approach along with the system replication. So this is an extended solution to system replication where as a simple setup we will have site A and site B. Site B is getting replicated from information of site A, and in case if you want to do an upgrade, be it hardware or software of site A, which is the productive system, then what we can do a takeover of primary to secondary, where secondary can act as the productive system, and then do the upgrade of the primary. So before doing this, what we do is we upgrade the secondary to the target level what we want, and then take over and then do the upgrade for the primary, and we can fall back where we use the actual primary for the productive environment. So once the replication is set up, we have continuous log shipping available to the secondary. What we can do for a simple upgrade procedure, we upgrade the secondary first using stbupd program with the option import content is equal to off, where we don't import the content. So without the content, we are upgrading the system. So once the secondary system is upgraded to the target level that we want, we choose to perform a takeover to secondary. And now the secondary would act as the productive system. And then upgrade primary to the same level as secondary. Should make sure we can upgrade primary to the same level as secondary, then perform a fallback to original primary system with new takeover. So again, we are back to original stage where primary is delivering the productive environment and secondary is acting as the standby. So that's how we can do any sort of upgrades, be it hardware or software, using the system replication technique. So with this, we have come to the end of this topic. Here we have understood how high availability and disaster recovery procedures help in continuous business availability.